Okay, now we're going to talk about section 2.5, transformation of functions. I'm going to assume that you have read all of the section and you understand the different transformations of functions and how those alter the equation of a function. I want to answer some frequently asked questions for you that sometimes pose challenges for students in my experience. The first question that I often get is, why is the graph of the function g of x equals x minus 2 squared the graph of f of x equals x squared shifted right 2 units and not left, right? Okay, so to answer this question, we're going to recall that x is an input to both f and g here. Okay? So we're going to examine which inputs give me the same outputs for f and g. Okay? So I'm going to make two charts. I'm going to say the input and then the f output. And I'm also going to look at inputs and outputs for g. Remember, f is x squared, g is x minus 2 squared, the shifted one. If I input 0 into f, I get 0. 2 gives me 4, and negative 2 gives me a positive 4. Now I'm going to look at which inputs, I'm going to try to figure out which inputs give me the same outputs for g. So how do I get a 0 for g? With what input does that give me? A 0. What input gives me a 4 as an output for g? And what input gives me a 0? Well, we can figure this out by taking our function and setting it equal to each of these outputs. If I take x minus 2 squared, set it equal to 0, I can say it's true then that x minus 2 is equal to 0, or the square root of 0, which is 0, and x is equal to 2. So the input that gives me the output 0 for g is 2. Then if I take my function again and set it equal to 4, x minus 2 squared equals 4 means that x minus 2 is either plus or minus the square root of 4, which is 2. So I get two separate equations, x minus 2 equals 2, or x minus 2 equals a negative 2, and then solving each of these, I get x equals 4, or x equals 0. So notice that if I plug in the input 4, I get 4 as an output, or 0 gives me 4 as an output. Now what we're going to do is we're going to compare these two lists. And we're going to notice something. In each case, the input that gives a value for g is always 2 more than the input giving the same value in f. So for instance, to get a 0 in g, we have to put in 2. That 2 is 2 more than what we must put into f to get the same value, 0. To get g equals 4, we have to put in either 4 or 0 in g. And to get the same output in f, 4, we have to put in either a 2 or a negative 2. So in each case, the input giving us the same output for f and g is 2 more for g than f. 2 is 2 more than 0. 2 is 2 more than 0. 4 is 2 more than 2. 0 is 2 more than a negative 2. So another way to say this is that to achieve the same output, or y value, to achieve the same output, which we know is a y value, in g of x, which is x minus 2 squared, we have to put in an input. We have to use an input that is 2 more than what we used in f of x equals x squared to get that output. Yeah. So we shift right, because where are x values 2 more? Well, input values, pardon me. Where are input values 2 more? They are to the right. Here's our original f. Goes through 0, 0, 1, 1 for sure, and 2, 4 also, right? To get 4, in G, we see that we have to put in 4. Here, let me erase this mark. It's kind of 2. Let's just call this 2 and 4. And then we'll do 4. To get the same output here, we had to put in 4 as the input in G, or 0. So it turns out that this shifts the graph 2 to the right. Okay, the second question that often comes up is in which order do we apply transformations? In which order do we apply transformations? It's always good to use a consistent order. So you need to do reflections first, then compressions and stretches, and then finally shifts. To take a look at this in action, we're going to look at an example where a graph of a function, we don't know its equation, is given. And we're going to draw from that, we're going to draw the graph of -2 times f of x plus 1 minus 3. This f here is the same f as this one. So what we're saying then is that we have some function f, and I'm going to give you its graph in a moment, and some things have happened to it, right? This negative out front says that it's been reflected over the x-axis. This 2 out front tells us that it's been stretched vertically by a factor of 2. This 1 being added to the x says that it's been shifted left 1 unit. And this 3 subtracted from the entire function tells us that it's shifted down 3 units. All right. Now what does our original function look like? Well, it's going to go through the points -2, 0, and -1, 1. I'm sorry, -1, -1, as well as 0, -1, and 1, 1. Also 2, 0, and that's where our function's going to end. So we're going to use a function that's just composed of some straight line segments to make this process Pretty easy to see. Okay, so this is our function f, our original function, f of x. Now we're going to apply all of the transformations in the order in which I suggested. First, we're going to reflect over the x-axis. Then we're going to stretch by a factor of 2. And then we're going to do shifting, and we might as well do it in this order, but it really doesn't matter. We're going to shift left 1 and shift down 3. Okay, so the first thing we're going to do is reflect over the x-axis. It's often it's much more straightforward to do this sometimes by doing one step at a time and drawing a new graph each time. So if I take my original f of x here and reflect it over the x-axis, what that means is that all of the y-coordinates are going to change signs. They're all going to become their opposites. Now at 2, 0, negative 2, 0, the opposite of 0 is still 0. So negative 1, negative 1 will still have x-coordinate negative 1, but it's going to flip over the x-axis to become a y-coordinate of positive 1. 0, negative 1, similarly, is going to come up and become 0, positive 1. 1, 1 will flip over and become 1, negative 1. And 2, 0, because the opposite of 0 is still just 0, will stay the same. So now we can see that our function looks very similar, except that it's been flipped over. So this function we could call minus f of x. Now the next thing we're going to do is we're going to stretch by a factor of 2. Stretch by 2. In practice, that means that we're going to multiply each y-coordinate by 2 because it is a vertical stretch. So again, all of our x-coordinates are going to stay the same as what they have been. We're just going to stretch the y-coordinates of our second graph of minus f of x, multiply them each by 2. Okay, so again, multiplying 0 by 2 leaves us still at 0. But if we multiply a 1 by 2, our point negative 1 becomes negative 1, 2. Similarly, we get a point at 0, 2. 1, negative 1 comes down here to 1, negative 2, and 2, 0 stays put. So now we have a stretched out graph. We could call this graph minus 2 f of x. Then we can shift 1 unit left. Which means we're going to subtract 1 from each x-coordinate. So instead of negative 2, 0, we'll be at negative 3, 0. And we'll be at negative 2, 2. And we'll be at negative 1, 2. And we'll be at 0, negative 2. As well as 1, 0. Now the final transformation that's happening is that we are shifting down 3 units. So we'll take our last graph and shift everything down, which means we're going to subtract 3 from each y-coordinate. That puts us at negative 3, negative 3, and negative 2, negative 1. As well as negative 1, negative 1, 0, negative 5, and 1, negative 3. And this is our final graph